Okay, we've seen how aldehydes and ketones can undergo nucleophilic addition with hydride ions, um, and now we need to look. The other nucleophile we need to consider is the cyanide ion. Okay, so cyanide ion, you have a triple bonded carbon to a nitrogen, and it's going to have one. So there's the carbon's 3 of its electrons in the triple bond, one there, and then it's got another electron there. The cross, which it is taken from somewhere else, doesn't really belong to it, and so the whole thing has got a negative charge. Okay, so there's just a couple of things we need to talk about the cyanide ion, right? So cyanide, it can be provided as potassium cyanide, that's KCN, and that's useful because it's an ionic solid. It's obviously non-volatile. So it's, even though the cyanide ion is very poisonous, it's cyanide. If you do biology, it's because it inhibits the last enzyme in the electron carrier chain, where the electrons are passed on to oxygen in the mitochondria. So it's extremely toxic, but it's reasonably safe to use if it's an ionic solid, because as long as you don't drink it or whatever, then it's not going to poison you. We also have, though, is if you like, this is the salt, but we have the acid, which is HCN. Now HCN so the bonding in that would be like this. This is a simple covalent molecule, which is not very big. It's a gas at room temperature. That means it is very dangerous, because you can breathe it in, so you don't have to consume it or anything, and it'd be very poisonous. So it's very difficult to work with hydrogen cyanide, because it is a gas and it's very poisonous. So I think usually you were going to use potassium cyanide, and in the last topic we've used potassium cyanide when we react with haloalkanes. But we see here there's some problems using potassium cyanide. If you have a potassium cyanide solution, it is about, in water, it's about pH 12. It's very alkaline. Why is it so alkaline? Is because HCN is a very weak acid. So we think of this equilibrium here, HCN is going to H plus and Cn minus, right? This equilibrium is way over to the left, okay? Because it's not a very good acid. That means that this cyanide ion, because this equilibrium is way over to the left, is reasonably good at accepting H plus ions. And if it gets them from water, it will take an H plus off water, you get OH minus made. So that is why potassium cyanide solutions are alkaline. And as we will see, you can't use potassium cyanide solution in this reaction because of the fact that it's alkaline. Okay, so let's have a look at what happens here then. Okay. Right, so we've got, let's just have the aldehyde, and right, we're going to react this with a cyanide ion. So that's delta positive there. Okay, so if we wanted to use the cyanide ion, would we use KCN or would we use HCN? Well, obviously we would use KCN because HCN hasn't got any cyanide ions because HCN is covalent, isn't it? So for this, we'd use KCN. So let's see what happens. The first step is that pair of electrons goes onto that carbon. That carbon's now forming 5 bonds, so the pi bond has got a break here. We're going to form that negative charge there. We've got our H and we've got our new cyanide group stuck on there. It's now a nitrile, isn't it? Now the final step in this mechanism, of course, is this this O minus has got to pick up an H plus from somewhere. So let's do that in blue. Okay, so the final product is going to be this, which has got 2 functional groups in it. It's got this OH, an alcohol, and it's also got a cyanide group in it. We'll talk about what we call that later, but let's just think about this step here. You can't have it too alkali. It's got to be neutral, really, okay? If it's too alkaline, it's going to be very difficult. There's going to be too much OH minus about taking all the H pluses. So this last step isn't going to occur. So there's a problem here, is because, as I say, here, I said we needed KCN. But here, I said you can't use KCN because it's too alkaline. And that would stop the reaction happening. So the conditions, and this is what the conditions are, KCN in KCN, sorry, followed by HCl. And if you like, so the KCN is needed for this first step here, yeah, and the HCl is needed to provide, you need some H pluses there. Okay, so that's the conditions they want you to write down. You've got to say that. What you can say is you can say or HCN. KCN followed by HCl is equivalent to HCN, but you can't actually add the HCN at first because it's a gas and it's poisonous. So really what happens is it's KCN followed by HCl. Apart from this little confusing bit here, the conditions, the reaction mechanism is exactly the same as with the hydride. And of course, this carbon here is asymmetric, isn't it? And so you will get a racemic mixture, just like you did with the hydride. Okay, and let's think about what we call these. So this thing here has got 2 functional groups in it. 2 functional groups. It's got an alcohol and a nitrile. This bit is the nitrile group. Okay, so what would we call this? We'd call it, well, it's 1, 2, 3, so it's propane nitrile. And because it's got this alcohol group on it, well, we can't call it propane nitrile, so we have to call it 2-hydroxy. 2-hydroxy propane nitrile. Okay, and the general name for these kind of compounds are hydroxy nitriles. Okay, so what I'll do is I'll before we finish this video is I'll just draw a series of some aldehydes and ketones, and then we have to try and work out what we'd call the hydroxynitrile formed and the structure of it. So, so let's do that. So let's do butanone. Let's do propanone. And let's do propanal. Okay, if you want to pause the video now, and then you can write down the structures and then try and name them. Or you can just see what the answers are. Right, so this one, we're going to get this one, we're going to get and the final one, we're going to get okay, let's try and name these. I'll start off with the last one because that's the easiest one. Okay, so this is, we're thinking here, this is the nitrile group, okay? So, and that's got to be on carbon atom number 1. So if the numbers in that way, 1, 2, 3, 4. So we would call this 2-hydroxybutane nitrile. This one is a bit tricky now because, well, we've got to consider that to be the N carbon. So this is going around a bit of a corner, isn't it? So that's going to be propane nitrile, and it's going to be 2-hydroxypropane nitrile. But it's also got a methyl group, hasn't it, attached to carbon atom number 2. So we're going to call it 2-hydroxy 2-methyl propane nitrile. And I think it's the hydroxy comes first there because this is a functional group, whereas the methyl isn't, so it gets preference. So it's not 2-methyl 2-hydroxy, it's that way around, I believe. This one here, right, so the longest carbon chain, this is more tricky, right? So we're going to have 1, 2, 3, 4. Well, it's going to be you've got a methyl group which is stuck onto carbon atom number 2, haven't we? And we've got the hydroxy there as well. So it's going to be 2-hydroxy 2-methyl butane nitrile. And I think it's a little bit confusing that because, you know, we've changed the numbering of the carbon atoms from the, you know, really you would call this one, you know, 1, 2, 3, you'd number it that way around, wouldn't you? And we've changed that numbering. You'd call that butanone. So that's the tricky thing. But remember, these hydroxynitriles are always going to be 2-hydroxy something or other, okay? Because this, well, because the nitrile carb is now number 1, and the alcohol has come from the carbonyl, which is next door to that.